I want to solve this interesting problem related to convolutions, Fourier transforms, and distributions. In particular, the first thing that we will do here in this exercise that seems quite complicated, but actually it is not so complicated if you know how to deal with the Dirac delta, convolutions, and the Fourier transforms. But anyway, let me explain the first step that we can take to solve this problem. The first thing that we can do to simplify the integral on the left is to integrate out this Dirac delta by using its properties. In particular, we can integrate over y, for example. And as usual, when we have a function that multiplies a Dirac delta, so this is the function that depends on t, y, and z, we can evaluate the function at the peak of the Dirac delta. So if we integrate over y, there is a peak at y equal to x minus z minus t. So this is where the Dirac delta is located in y. So when y is equal to x minus z minus t, we have an infinity due to this Dirac delta. So basically we can evaluate this function f of y at this peak. And then the integral over the real axis of the Dirac delta will give us 1. So basically we are left with the integral from minus infinity to plus infinity, another integral from minus infinity to plus infinity, f evaluated at x minus z minus t, then we have f of z e to the minus t squared over 2 divided by the square root of 2 pi, which is just a Gaussian density. So this is a Gaussian probability density if you want. Then we have dz dt. This must be equal to another Gaussian probability density with a different variance. So we have e to the minus x squared divided by 2 sigma squared over square root of 2 pi sigma squared. And the problem set tells us that sigma must be greater than or equal to 1. We will see why this must be the case, but for now we were not really interested in this. We will see that this has to do with the fact that our function f of x should go to 0 as the mode of x goes to infinity. So we will see that there would be problems if this weren't true. Anyway, at this point, let's focus on the integrals on the left. If we focus on them, and if you look at them properly, you can see that there is a triple convolution. There is a convolution between the function f and the function f and this function here. So if you want, you can also work out the details, and you can substitute, for example, the inverse Fourier transform. So we can define f in terms of the inverse Fourier transform, and you can substitute it here. Or another thing that you could do is you can take the Fourier transform on both sides of this equation over the variable x, because the one on the right and the one on the left, especially let's take a look at this one on the left, you can see that the variable which the function depends on is x, because z and t are just dummy variables. And of course that must be the case because the one on the right is also a function of x. What I'm going to do, so I'm going to tackle the problem in the following manner. I'm going to take for granted that this is a triple convolution, and you know the theory of convolutions, and I'm going to apply the properties of convolutions. These properties are very interesting properties, especially because they will simplify a lot when you go to the Fourier domain. So in particular, I'm going to take the Fourier transform on both sides of this equation, and the function that we will get on the left will be a product of Fourier transforms of these three functions here. So we have the Fourier transform of this function here, f, and I'm going to call it, for simplicity, f hat, that will depend on some variable k. Then we have the Fourier transform of this, and we still have to evaluate it at k. This has to do with the properties of the convolution. And then we have to take the Fourier transform of this. Now I'm going to to write it in the following fashion, we have the Fourier transform of this function, e to the minus t squared over 2 divided by the square root of 2 pi, and then of course also this one must be evaluated at k. And then this must be equal to the Fourier transform of the Gaussian density that we have on the right, e to the minus x squared over 2 sigma squared divided by the square root of 2 pi sigma squared. And what I'm going to do now is I'm going to give you just the formula for the Fourier transform of this Gaussian integral. So basically this Fourier transform will give us a Gaussian integral that can be evaluated. So I'm going to give the formula because I'm not going to treat that, to deal with that in this video. We have the Fourier transform of, let's write it like this, e to the minus ax squared, and then this will give us a function of k. So we are transforming from x to k. Whereas, for example, here, when I write it like this, I'm assuming that we are transforming from t to the variable k. So sometimes you can also see this like this, f sub t to denote the fact that we are transforming the variable t. But I'm not going to, let's say, clutter the notation. I don't want to make it untidy. I want to keep it clean. So this is the way I want to write it in. And on the right, you can see that we are transforming from x to the variable k. So let me also write it here. We have the transform over the variable k. The formula for this Gaussian term is something like this. You have the square root of pi over a, e to the minus pi squared k squared over a. Now let me tell you that with this Fourier transform here, you might have different definitions. And these definitions might differ in the constant that appear before the transform. So you have a multiplicative constant, or you might also have a multiplicative constant in the argument of the exponential. For example, I have taken this formula from Wolfram, so you can see here that, so let me enlarge this picture. This is just a screen capture, it's a screenshot. You can see that the definition that Wolfram is using here is this definition here, where you have the 2 pi in the argument of the exponential, and you don't have any constant that multiplies the transform. Well, you have to keep in mind that this is not really important, because at the end of the day, even if we use such a formula, which might differ in the case you use a different definition of the Fourier transform with different constants, at the end of the day, we still have to go back. So we have to take the inverse Fourier transform. So as long as you define your transform and the inverse transform properly, you're going to get, of course, the same result, because remember that we want to find the function f of z or f of x. So we are in the quote-unquote spatial domain, in the space domain, if you want. Whereas here we are in the frequency domain. And you might define a frequency multiplied by 2 pi, like 2 pi k, and in this case k, for example, is hertz, so it is measured in hertz, whereas you might have a frequency measured in radians per seconds, for example, so omega, and this is defined in a different manner without the factor of 2 pi. So of course these factors would change a little bit the formula, but as I said, the result should be independent of the definition that you use if you're doing things correctly. So we are going to use this formula. So I will take this for granted, and I will use this formula to calculate these transforms. So basically, here we can put them together. So we have f hat of k squared. Then we have the Fourier transform of this. You can see that we have a equal to 1/2 here. So the square root of pi over a will become the square root of 2 pi, so this will cancel this term here. So we are left with e to the minus 2t squared, and we have to evaluate it at k, so this is 2k squared. And we also have pi squared, because we have this term here. Then on the right, we have the square root of pi over a, and if you take a look at it, a is equal to 1 over 2 sigma squared, so we get the square root of 2 pi sigma squared, which will cancel this term here, so they will cancel. And therefore, we can write e to the minus 2 sigma squared k squared pi squared. And at this point, we can take the square root on both sides, so we can get rid of these two, and these two, and then we can take this term to the right hand side, so we can write half hat of k equal to e to the minus, let's put pi squared here, sigma squared minus 1 k squared. And basically we can take the inverse transform to obtain the function f of x. So the function f of x is the inverse transform of this Gaussian term. We have a formula for that. So it's the inverse transform of e to the minus pi squared sigma squared minus 1 k squared. And at this point you can also see why we have to consider sigma squared greater than 1, or in particular sigma greater than 1, because otherwise this term here would be negative, and that would give us problems. And in particular, those problems are related to convergence of the integrals, related to the transforms. So we have to assume that sigma is greater than 1, and usually sigma is the standard deviation. So it's the standard deviation of a Gaussian function, a Gaussian probability density function. So that's why we are considering sigma greater than 0, but at the same time, it should also be greater than 1, greater than or equal to 1. And then here, when I consider the inverse transform, we get the following. So first, let me multiply this by a over pi, the square root of a over pi, so we have f inverse, and I'm calling this guy here 1 over a, so I have f inverse of the square root of pi over a e to the minus pi squared over a k squared, and then I know what the inverse of this function is, because I have written the inverse here. So the inverse would be exactly this function here, e to the minus a x squared, where a is equal to the inverse of this. So all in all, what I get is the square root of 1 over pi sigma squared minus 1 e to the minus x squared divided by sigma squared minus 1. And this is another Gaussian probability density. We could have guessed this form, the Gaussian form, right from the start, because as you can see, after we integrate out this Dirac delta, we get a convolution of 3 functions, and we get a Gaussian density. We start from a Gaussian density here, and it makes sense that these 2 functions here are also Gaussian functions, because the convolution of Gaussian functions will give us a Gaussian function. That's the only function whose finite number of convolutions will give us a Gaussian function. So we must be a little careful here when we say this. And this is also related to the central limit theorem, especially if you consider an infinite amount of convolutions. When you have different distributions which are not necessarily Gaussian distributions, Well, you convolve all these distributions, you are going to get closer to the Gaussian distribution under certain assumptions. So this also has something to do with the central limit theorem. I'm not going to get into the details of that. But here you see the result because we have proved this. And you can also see why we have to assume that sigma squared or sigma should be greater than 1. Or if you want, we can also be a little less strict and also consider the point sigma equal to 1. In that case, we have to consider a certain limit where this Gaussian distribution will tend towards Dirac delta, because in that case, these, the standard deviation of this Gaussian density would become 0 or very close to 0. And in that case, we have like a Dirac delta because we have no uncertainty around the average value, if you want, and that's it.